Hi there. So today we're going to be going through the class test 3 practice paper. Okay, so the solutions are available as well on Learn 2022 if you want to read through them later. Okay, so let's go through question 1. Okay, and 1.1. So the question says plot the graph of r equals 3 over 1 plus 2 sine theta. And then we have the interval 0 less than or equal to theta, less than or equal to pi over 2. So we are sketching in the first quadrant. Okay, so the first things that we need to do is find the x-intercept and y-intercepts to give us an idea of what this graph is going to look like. So for the x-intercept, that's going to correspond to r of 0. If we substitute that in, we're going to get 3. So if we go along the x-axis, we move 3 along the x-axis. So that gives us the point 3, 0. The other x-intercept, that will happen at pi. Okay, so we flip around 180 degrees. So r of pi is going to give us 3. So we're moving in the negative x-axis 3 units. So that's going to be minus 3, 0. Okay, but we're not really interested in that point because, again, we're only interested in 0 to pi over 2. But I recommend finding all the intercepts to give an overall picture of what it looks like. And then you can sketch the part that's asked of you. Okay, so y-intercepts. Okay, so that's going to be r at pi over 2. So we can substitute that in and we're going to end up with 1. So that gives us a y-intercept of 0, 1. And r at 3 pi over 2, that's going to be minus 3. So 3 pi over 2 means we're moving down. But since the radius is negative, that means we're going up in the other direction. So that's going to be 0, 3. Okay, so we've got all of our intercepts. Now, what kind of graph is this? Well, first note that we have this 2 over here. So we know it's going to be a hyperbola. Next, it's sine theta. So that tells us we're dealing with a horizontal directrix. And this 3 tells us that it's a positive one. So the 3, let's just make a note here, the 3 and the sine theta, that tells us that we have a horizontal positive directrix. Okay, so if we do a little sketch, it's going to be something like this. Okay, so that's going to be our directrix for the hyperbola. And we know it's a hyperbola because there's a 2 in front of the sine theta. So it's going to be something like this. Okay, but that's just a very rough sketch. Let's do it a bit nicer. Okay, so let's put in our axes. Okay, we know our intercepts are going to be 3, 0. So that's somewhere over here, let's say. Minus 3, 0, that's somewhere over here. Okay, now the labeling doesn't have to be too accurate, but as long as you label your points 3, 0, minus 3, 0, then I know what you mean. But if you just put a dot, then I don't know what you mean. Okay, then the y-intercept 0, 1, let's say that's somewhere here. And 0, 3, that's going to be somewhere here. Okay, so we can now connect these points because we know the general shape. It looks something like that in blue. But remember, we're only dealing with the graph from 0 to pi over 2. So that means it's going to be this part over here, like that. Okay, and then the asymptote line, that's going to be somewhere along here. So that top branch, that's going to follow the asymptote line. Okay. Let's look at 1.2. So we have the same function, okay, r equals 3 over 1 plus 2 sine theta, but we want to know what is the Cartesian form of this. So from polar form to Cartesian form. Okay, so let's have a look at that. So we start with r equals 3 over 1 plus 2 sine theta. And we know that x is r cos theta and y is r sine theta. So we're going to be using that to figure out what to do. Okay, so let's get rid of this fraction here by multiplying both sides by this denominator. So we're going to have r 1 plus 2 sine theta is equal to 3. Then we can separate this out. So r plus, let's write that as 2r sine theta is equal to 3. Okay, now we want to get the r by itself, because remember that r squared is x squared plus y squared. Okay, so we need to square the r term, but it's better to do that if it's by itself. So r is equal to 3 minus 2r sine theta. And now we can square both sides. So r squared is going to be 3 minus 2r sine theta squared. So r squared is going to be 9 minus 6r sine theta plus 4. And then I'm going to put this in brackets, r sine theta squared. Okay, now we can put in all of our conversion terms. So r squared, that's going to be x squared plus y squared. That's equal to 9 minus r sine theta. That's going to be y. And r sine theta squared is going to be y squared. Okay, now we can take all of the x and y terms to one side. So we're going to have x squared plus y squared minus 4y squared plus 6y is equal to 9. Okay, then we can simplify that because y squared minus 4y squared is minus 3y squared. And then we have plus 6y is equal to 9. So this y squared and the y term, we can combine those if we do completing the square. So x squared minus 3. And then we can write the remaining terms as y minus 1 squared plus 1 to cancel that, that extra term that we've got there. And this is equal to 9. Okay, so we just factored out the minus 3, and then we completed the square. Okay, next we can simplify this. So we have x squared minus 3y minus 1 squared minus 3, and that's equal to 9. Here we can take the minus 3 over. So we have x squared minus 3y minus 1 squared is equal to 12. And lastly, we can divide through by 12 because we want the right-hand side to be 1. Okay, that gives us the standard hyperbola form. So we're going to have x over root 12 squared. So that's something like the x squared over a squared term. Minus, and then we're going to have y minus 1 over 2 squared. So that's going to be our y squared over b squared term. And that's equal to 1. Okay, so this is the standard form for the hyperbola. Okay, so that's the x over a, all of that squared, minus y over b, all of that squared is equal to 1. But we've got this extra minus 1 here because it's been shifted from the origin. Okay, but this right-hand side, this is the standard form if it's at the origin, and then you can apply the shifts to move it away from the origin. Okay, let's have a look at question 2. so question 2 is about complex numbers and applications of complex numbers. So 2.1, we have 2 minus 2i to the power 4. And we want to write this in the form a plus rb. Okay, so if we're dealing with exponents here, raising a complex number to some exponent, it's better to do that in polar form, okay, because of that exponential. It's easy to do exponents with that. Okay, so we need to find the magnitude of this complex number. So that's going to be the square root of 4 plus 4. So that's the square root of 8. Okay, and then the angle or the phase that it makes, that's going to be arctan of minus 2 over 2. So that's arctan of minus 1. We can write that as minus pi over 4. Okay, so that says that z is equal to root 8 e to the minus r pi over 4. So that's the same complex number, but now in polar form. Now that it's in polar form, we can raise it to the power 4 much easier. So z to the 4 is going to be root 8 e to the minus pi over 4 to the 4. And then the 4 distributes onto those two terms. So it's going to be 8 to the half to the power 4. So that's going to be 8 squared. And e to the minus, sorry, there's an r there. E to the minus r pi over 4 times 4 is just e to the minus r pi. So 8 squared, that's going to be 64. E to the minus r pi, that's going to be minus 1. So it's minus 64. Okay, so that is this complex number raised to the power 4. Okay, the next question is to find the 3 cube roots of z equals minus 3. So 2.2. Find the 3 cube roots of z equals minus 3. Okay, like we had before, this is going to be easier to do in polar form because we have to take certain exponents. So let's write this in polar form. Z is going to be, the magnitude of Z is just 3, and the phase is going to be pi because this minus 1 term in front can be written as e to the r pi. So it's going to be 3 e to the r pi. Okay, that gives us our minus 3 back. Now, we don't want Z, we want Z to the 1 over 3 because it's the cube roots. So Z to the 1 over 3 is going to be 3 to the 1 over 3. And then we're going to have e to the r pi plus 2k pi over 3. And remember, we add the 2k pi because the exponential function is 2 pi periodic. Okay, where k is some integer. And since we're finding the 3 cube roots, k is going to be 0, 1, 2. That gives us 3 of them. So if we substitute 0, we're going to get W0. That's just how we write the roots. So if z is the original complex number, we use W0, W1, W2 to represent the cube roots. So that's going to be 3 to the 1 over 3. And if k is 0, it's going to be e to the r pi over 3. Okay, and we can easily convert that into Cartesian form because we know what cos of pi over 3 and sine of pi over 3 are. So that's going to be 3 to the 1 over 3, 1/2 plus I root 3 over 2. So that's just the Cartesian form of that root. Okay, what about W1? That's going to be 3 to the 1/3 e to the r pi plus 2 pi over 3. Okay, and that's going to be e to the r pi, which is just minus 1. So it's going to be minus 3 to the 3rd. And the last one, W2, that's going to be 3 to the 1/3, e to the r pi plus 3 pi all over 3. Okay, so that's e to the 5 pi over 3. Sorry. Okay, so we can simplify that to 3 to the 1/3 half minus I root 3 over 2. Sorry, that's if we substitute 2, that's going to be 4 pi. Sorry, not 3 pi, that'll be 4 pi. Okay, and then 4 pi plus pi, that'll be our 5 pi over 3. Okay, then that's our 3 roots. So we get 1, 2, and 3 cube roots. Okay, 2.3. Okay, so this question asks us to find the value or values of log 1 minus r. Okay, so to answer this, we first need to write this in polar form because we need the magnitude and we need the phase. Okay, those are the two things that we need when writing out the log of a complex number. So let's find the magnitude. So z is going to be the square root of 1 plus 1, that's just root 2. Then the phase, so theta is going to be arctan of minus 1 over 1. That's going to be minus pi over 4. Okay, so we've got the magnitude, we've got the phase. We can write out what our answer is now. So log of 1 minus r is going to be the natural log of the magnitude, because the magnitude is always a positive real number. So natural log of root 2 plus r times the phase. So that's minus pi over 4. And remember that the log of a complex number is a multi-valued function. So we need to add 2 pi k, where k is some integer. Okay, for every value of k, we get a different value for the log. Okay, and if you want to simplify this, log of root 2, we can write as half log 2 plus r minus pi over 4 plus 2 pi k. Okay, but that's not super important. Okay, 2.4, we want to write cos of 3 theta as the sum of powers of sine and cosine. Cos 3 theta. Okay, we want to write that not in terms of this 3 times the angle. We just want it in terms of cos theta and sine theta. So what we do is notice that if we have cos of theta plus r sine theta to the 3, that's going to be cos 3 theta, which is what we want. And r sine 3 theta, we don't want that, but that just comes with the calculation. So if we can calculate the left-hand side and look at the real part, then we'll get the real part of the right-hand side, which is what we want. Okay, so let's calculate this binomial expansion here. So we're going to have cos theta plus r sine theta cubed. Okay, that's going to give us cos cube theta plus, and then our first binomial coefficient, that's 3. That's cos squared theta r sine theta plus the next binomial coefficient, that's going to be 3 again. But now we have cos theta r sine theta squared, all of it squared, the I is included, and then plus I sine theta cubed, and again the I is included, so all of it is cubed. Okay, now we can simplify the r squared and the r cubed. So we're going to have cos cubed theta plus I 3 cos squared theta sine theta. And then the r squared is minus, so minus 3 cos theta sine squared theta. And r cubed is minus r, so we have minus r sine cubed theta. Now, we were interested in cos 3 theta, which means we look at the real parts. That's that term and that term. Therefore, cos 3 theta is going to be cos cubed theta minus 3 cos theta sine squared theta. Okay, and that's our final answer. Okay, question 3. We have 3.1. Oh, sorry, 2.5 we still have to do. Find the value or values of z such that cos of z is equal to 2. Okay, so we want to solve for cos of z being 2. Now, we know there's no real solution because cos of, let's say, x, where x is real, is always bounded between -1 and 1. So there's no way for that to be real. So we're going to have some complex number solution, okay, for z. Okay, we may have more than one solution. Okay, so what we do now is we rewrite cos of z in terms of the exponentials, because remember cos, that's just the name that we give it. If we're dealing with complex numbers, we need to write it in terms of the exponential form, okay, for us to actually do anything. So this is going to be 1/2 e to the rz plus e to the minus rz, and that's equal to 2. Okay, so now we can do some work with this. So this is going to be e to the rz plus e to the minus rz is equal to 4. Now we don't want to work with e to the rz and e to the minus rz. So let's multiply through by e to the rz. So we're going to have e to the rz squared minus 4e to the rz plus 1 is equal to 0. Now this is just a quadratic if you imagine e to the rz as another variable. So we can solve for it using the quadratic formula. So e to the rz is equal to minus b, so minus 4 plus or minus the square root of b squared, so that's going to be 16, minus 4ac, so that's just minus 4. Okay, all over 2. Okay, we can simplify that. So e to the rz is equal to 4 plus or minus 2 root 3 all over 2. And that simplifies to 2 plus or minus root 3. Okay, so we get 2 solutions for this e to the rz. Okay, but we don't want e to the rz, we want just z. So how do we undo exponentiation? We take the log on both sides. So rz is going to be the log of 2 plus or minus root 3. Okay, now that log is interpreted as the complex log, but if we take the complex log of a real number, then it just becomes the natural log. Okay, so it's like the subset of the domain. If it's a general complex number, then we use log. If it is specifically a real number, then it just becomes the natural log. So here we have rz is equal to the natural log of 2 plus or minus root 3. And remember, the exponential is 2 pi periodic. So we need to add I to pi k. Okay, because of that periodicity, we need to include that. Next, we've got rz, but we actually want z. So let's multiply through by r. So we're going to have minus z is going to be I, natural log 2 plus minus root 3, minus 2 pi k. And then finally, we can multiply through by minus 1. And we get z is equal to 2 pi k minus I, natural log of 2 plus minus root 3. Okay, so you can pick the plus term, and then you have infinitely many solutions with each value of k, and you can choose the one with the minus, and then again you have infinitely many solutions with your pick of k. Okay, so that's why it says find the value / values. So in this case, there are many values. Okay, so now question 3 is on Taylor series. So let's have a look at that. Okay, so we want to find the Taylor series of x sine x centered at x equals 0. So Taylor series of f of x is x sine x at x equals 0. Okay, now, like I said before, if we have these complicated functions, so either a composition or a product, then there are certain things we can do to make it easier. So in this case, we have a product of two things. We've got x and we've got sine x. So instead of finding the Taylor series of the product, we can find the Taylor series of just sine x and then multiply the result by x. Okay, that makes things a whole lot easier. So if we let g of x be sine x, then we can find the Taylor series for g and multiply everything by x, and then we get our f of x. Okay, so if g is equal to sine x, then we can go through all the derivatives to see what those coefficients are. So let's start. G of x is sine x, and we want to find the Taylor series at x equals 0. So g of 0, that's 0. G prime is going to be cos x. So g prime at 0 is going to be 1. G double prime at x, that's going to be minus sine x. And if we evaluate that at 0, we get 0. Okay, so you might be seeing the pattern so far. Let's do one more. G triple prime at x is going to be minus cos x. So g triple prime at 0 is going to be minus 1. So we see we have this alternating behavior between sine and cosine, and then again this alternating behavior between 1 and minus 1, because the derivative of sine gives us cosine, but the derivative of cosine gives us minus sine. So we have this alternating plus and minus as we go through the odd terms. So all of the odd derivatives have a non-zero value because all of the even derivatives end up being sine, and that gives us 0. So we go plus 1, minus 1, plus 1, minus 1 for all of the odd terms. Okay, so each odd term alternates between plus 1 and minus 1. So we can write g of x is equal to the sum k equals 0 to infinity of 1 over 2k plus 1 factorial. So remember, in the definition, it's the derivative evaluates at 0 divided by k factorial. But since we are only dealing with the odd terms, this factorial term has to be odd. So that's why we have 2k plus 1, because that's going to give us all of the odd numbers. Then we need to deal with this alternating sequence of plus 1 and minus 1. So we can write that as minus 1 to the k. Okay, so if k is 0, then that's the first one here. That's going to be a 1. And then when we get the next value, when k is, we can write it out afterwards. So minus 1 to the k, x to the 2k plus 1. Okay, so let's just write out a couple of terms. So when k is 0, we're going to have 1 over 2 times 0 plus 1. So that's 1 over 1 factorial. Minus 1 to the 0, that's just going to be 1. X to the 2k plus 1, that's just going to be x. Okay, then when k is 1, we're going to have 1 over 3 factorial. Minus 1 to the 1, that's minus 1. And then x to the 3. Okay, and then we can do one more. When k is 2, we're going to have 1 over 5 factorial. Minus 1 to the 2, but we can just leave that as plus 1. And then that's going to be x to the 5. And so on. Okay, so you see we only have odd terms, and they alternate between plus 1 and minus 1. They alternate between plus or minus. The actual coefficients are going to be 1 over the odd integers factorial. That's these coefficients here. Okay, but that's not our full answer. That's G. Remember, what we wanted is x sine x, so that's going to be x times G. So then f of x is x sine x, so that's x times G. So we can take our series expansion and just multiply through by x. So f of x is going to be x times the sum from k equals 0 to infinity, 1 over 2k plus 1 factorial, minus 1 to the k, x to the 2k plus 1. And now the x can just hop inside. So this is going to be the sum from k equals 0 to infinity, 1 over 2k plus 1 factorial, minus 1 to the k. And then multiplying by x just adds 1 to the exponent. So it's x to the 2k plus 2. Okay, so this is the series expansion for x sine x. Now, this is not part of the test, but if we had something similar, but instead of having a product of functions, we have a composition. So let's say we had f of x is sine x squared, for example, then instead of finding the derivatives of sine x squared, instead we can find this function g, which is sine x. Then f is just going to be g of x squared. Okay, so we already have the series expansion for g. So if we substitute x squared, what do we get in that case? So f of x is going to be g of x squared. So that's going to be the sum from k equals 0 to infinity, 1 over 2k plus 1 factorial, minus 1 to the k. Now, instead of x, we substitute x squared. So here we had x to the 2k plus 1. Now we can write x squared to the 2k plus 1. Okay, because we're doing a composition of functions. So this is going to be the sum from k equals 0 to infinity, 1 over 2k plus 1 factorial, minus 1 to the k, x to the 4k plus 2. Okay, so you see these are the two tricks that you can use to find the Taylor expansion of more complicated functions. So if it's a product, we can take the Taylor expansion of sine, because we know how to do that, and then multiply the result by x. In the second case, if we have to find the Taylor expansion of sine x squared, we don't do that. We find the Taylor expansion of sine, and then just substitute x squared. Okay, that has the same effect as finding the Taylor expansion of sine x squared. Okay, and then we get our same result here. Okay, so that's it for the questions. If you have any questions of your own, please let me know through email. Remember, you can also ask the tutors for help or you can post it on the class WhatsApp group, and maybe someone else can answer, or myself or the tutors can answer there as well. Okay, remember the test is tomorrow, so there's no revision session before the test. As soon as the tutorial starts, we'll start with the test, and then afterwards you can go. And just a note, for the collection of the previous assessments, you can collect them from our office throughout the day, and then after that, they go into storage. Okay, so if you do want to get your assessment, please make sure you collect it from our office before the test starts. Okay, I'll see all of you tomorrow.